Hello, welcome to today's lesson on heating and cooling curves. A heating and cooling curve is simply a graph of temperature and time that shows us how different substances change state, how their temperature changes as they're changing state. There are three main stages of matter: solids, liquids, and gases. All matter has kinetic energy, unless it's at absolute zero, but different states of matter have different amounts of kinetic energy. In a solid, the particles have kinetic energy and vibrate. There are strong forces that hold particles in places so they can vibrate back and forth and not slip past each other. As a result, solids hold their shape. In a liquid, the particles have more energy. Although the particles are still attracted to each other, the fact that they have more energy meant that they are able to slip and slide past each other. As a result, liquids are able to flow. Gas particles have a lot more energy. As a result, although they are still attracted to each other, they are able to move around much more freely from place to place. This means that gases are also able to flow. As well, because gas particles are much more spread out than solids or liquids, gases are able to be compressed or expanded to fill a container. Substances are able to change state from one state to another by adding or removing kinetic energy. Melting is the change of state from a solid to a liquid. Fusion is the change of state from a liquid to a solid. Sometimes this is called freezing. Vaporization is the change of state from a liquid to a gas, sometimes called boiling. Condensation is the change of state from a gas to a liquid. Sublimation is the change of state from a solid to a gas without being a liquid in between. And deposition is the change of state from a gas to a solid with one step, sometimes called sublimation, again without hitting the liquid phase. Since the particles in the substance in different states have different amounts of energy, heat must be added or removed in order for a substance to change state. Melting, vaporization, and sublimation all require energy to be added. Therefore, these are endothermic processes. Fusion, condensation, and deposition all require energy to be removed. Therefore, these are exothermic processes. Here's an example of a heating curve. Think about a block of ice at 20 degrees Celsius. What would happen if you started minus 20 degrees Celsius? What would happen if you started to heat the block of ice? At first, the temperature would rise. It would rise from 20 degrees Celsius to 0 degrees Celsius. At 0 degrees Celsius, though, something would happen. The ice would start to change state to form water. This is because 0 degrees Celsius is the melting point of water. It is also the freezing point if you're going the other way. Once the ice has melted, now you have water at 0 degrees Celsius. If you keep adding energy, the water will begin to heat up and the temperature will rise again. The temperature will continue to rise until the water reaches 100 degrees Celsius. Then, even if you keep adding heat, the water's temperature will not continue to rise. So when you have a container that has two states of a substance in it, the temperature will remain constant until the states are all the same. So the reason for the water to stay at 100 degrees Celsius while it's changing from a liquid to a gas is that 100 degrees Celsius is its boiling point, or the condensation point. This is where it changes from a liquid to a gas. All of the energy you are adding will now go into changing the state of particles, and the water will stay at 100 degrees Celsius until it is all a gas. Once the water has entirely turned into steam, if you continue to add energy, the temperature will start to rise again and the steam will get hotter. So here's an example of a cooling curve. So this substance we can assume is water because we can see the flat pieces at 100 and at 0, which is 100 and 0 are the condensing and freezing points of water. So from here to here, this H2O is in a gaseous form. Between here and here, it is now cool enough that it is condensing into liquid water. Between here and here, the liquid water is cooling down to 0 degrees Celsius. At this point now, the liquid water is freezing. So it's freezing into that solid ice, the solid water. If this cooling curve were to continue and we were to continue taking the kinetic energy out of the sample that we were looking at, the graph would more than likely go down after it had all been turned into a solid. Some important information. Although to keep it simple, the graph has perfectly straight lines. It is not unusual for the graphs to be curved. For every substance has its own freezing or melting, boiling or condensing points. Different conditions can change the freezing and boiling points of a substance. The two most common are pressure and the presence of a solute, like ice or like salt. So we salt our sidewalks so that the melting point of the water changes. Under certain conditions, substances can be in different states than what they should be at certain temperatures. Supercooled liquids are the most commonly seen example. Sometimes substances can change between solid and gas phase without being in a liquid phase. Remember, this is called sublimation. So now we're going to look at latent heat calculations. Just like we could calculate the amount of energy needed to change the temperature of a substance, we could also calculate the amount of energy to change a substance's state. We can do this using the idea of latent heat. The formula for latent heat is Q equals mL, where Q is the latent heat energy, usually in joules or kilojoules depending on the table that you're looking at. M is the mass, usually in kilograms, though it could be grams if the table that you're looking at uses grams. L is the latent heat of fusion or vaporization, and this comes from a table. Remember to be careful with your positive or negative signs. If you're looking at the heat of vaporization, but you're condensing, you're going to have to use the opposite sign. Same thing with the heat of fusion, but if you are melting, then you will again use the opposite sign. If you are unsure of this, think about your endothermic and exothermic reactions. If you are putting heat into your system and things are either melting or vaporizing, you are going to want to have heat going into your system. So you're going to want positive energies. If you are freezing or condensing, you are taking heat out of your system, so you are going to want a negative energy. All right, so let's do an example. Let's figure out how much energy you need to melt 250 grams of lead. So we're going to start by writing our formula down like we always do. So Q equals mL write down our knowns and unknowns. We don't know what Q is. M is 250 grams. L from my table is 20.4 kilojoules per kilogram. So immediately when I see this, I note that my mass is in a different unit than the unit I got from my table, which tells me I need to convert my mass to kilograms. Remember, to convert grams to kilograms, you divide by 1,000 or move your decimal point to the left 3 places. So I end up with 0.250 kilograms. Okay, I'll substitute my variables in. So Q equals ml. Q equals 0.25 times 20.4. When I do the math, I end up with 5.1 kilojoules. So it would take 5.1 kilojoules of energy to melt 250 grams of lead. Another example, how much energy is required when 1.5 kilograms of water is turned into steam? So it doesn't give me a starting temperature, so I'm going to assume that the liquid is already at the temperature it needs to start turning into steam, which means I can use the formula Q equals ml again. Okay, I'm going to go through and write my variables down again. So I don't know what my Q is, that's what we're looking for. My mass is 1.5 kilograms. My L is 2,260 kilojoules per kilogram. I'm going to take those numbers and sub them into my equation. Q equals 1.5 kilograms times 2,260 kilojoules per kilogram. Kilograms cancel out, so I know I'm on the right track. 1.5 times 2,260 is 3,390 kilojoules. So to create steam, water vapor out of 1.5 kilograms of water would require 3,390 kilojoules. All right, one last example. This one's a little bit of a doozy, but we'll work through it. There will be a question like this on your assignment. How much energy is required to turn a 2 kilogram block of ice at minus 10 degrees Celsius into steam at 120 degrees Celsius? So for this, we need to think about our cooling or heating graph. So this heating graph, we are going to be heating. We're going to be heating, then it's going to be melting, then we're going to be heating, then it's going to be boiling, and then we're going to be heating to our final temperature of 120 degrees. So for each of these chunks of the graph, we're going to have to be doing a different calculation. So there's 6 parts to this graph. 1, 2, 3, 4, 5. Sorry, 5 parts to this graph. So for part 1, which is the ice warming to 0 degrees Celsius. Okay, so for the ice to warm to 0 degrees Celsius, we're going to use our Q equals mc delta T formula. We're going to write down our unknowns and our variables, our knowns and unknowns. So we don't know the Q. The mass is 2 kilograms. The C of water is 4,180 joules per kilogram degrees Celsius. The delta T, remember, is TF minus TI. The final temperature is 0 degrees Celsius. The initial temperature is negative 10 degrees Celsius. So our change is then 10 degrees Celsius. We'll sub in our values. Q equals 2 kilograms times 4,180 joules per kilogram degrees Celsius times 10 degrees Celsius. Degrees Celsius cancel out, kilograms canceled out, so I am just left with joules. I am left with 83,600 joules. Let's convert that to kilojoules because that's a big number and I don't like big numbers. So we're going to convert to kilojoules by dividing by 1,000. So we go over 3 decimal points to the left. So we end up with 83.6 kilojoules. Circle that number. So that is the amount of energy I need to get from my beginning point to where my water is now melting. Okay, my second part now is where that ice melts. Okay, so for that, I'm using the formula Q equals mL. Knowns and unknowns. We don't know what Q is. Our mass stays the same. We're not losing water anywhere. Our L comes from our table. L is 334 kilojoules per kilogram. We do our math. Q equals 2 times 334 kilojoules per kilogram, which gives us 668 kilojoules. This is kilograms here. Kilograms cancel out. I end up with kilojoules. The second number I need to remember. So that is the amount of energy it takes me to get through this second part of my heating curve. Okay, so part 3. So the third part is where the water The water is warming to 100 degrees Celsius. Okay, so that I'm going to use my Q equals MC delta T. Okay, so how much energy it takes to raise a substance's temperature. Okay, rate my knowns and unknowns. We don't know Q. M is still 2 kilograms. Delta T is the T final minus T initial. So my final temperature is 100 degrees Celsius. My initial temperature was 0 degrees Celsius. So my change in temperature was 100 degrees Celsius. You do the math. Q equals MC delta T. I don't know why I wrote that again. I just did. So 2 kilograms. Oh, I didn't do C in here. My C is still 4,180 joules per kilogram degrees Celsius. So 2 kilograms times 4,180 joules per kilogram degrees Celsius. Multiply that by my change in temperature, which is 100 degrees Celsius. Degrees Celsius and the kilograms cancel out. So I do my math in my calculator, and I end up with 836,000 joules, even bigger than the last one. So I'm going to divide by 1,000 to get my kilojoules. So 836 kilojoules to heat my water up to its boiling point. Okay, so I have my first 3 parts done. Okay, now I need to figure out how much heat is required to heat this, or to turn all of the water into steam. This is part 4. Okay, so Q equals ML. Knowns and unknowns. Don't know Q. M is still 2 kilograms. Still haven't lost any of that water. L. The L now has changed because we're looking at the latent heat for steam now. So it's 2,260 kilojoules per kilogram. So I do my math again. Q equals ML, Q equals 2 kilograms times 2,260 kilojoules per kilogram. Cancel out my kilograms. And when I do my multiplication, I end up with 4,560 kilojoules. Almost there. One more part to my graph. So this last part, we've done 4. This last part here, as the temperature is rising to 120 degrees Celsius. So the steam heats to 120 degrees Celsius. So, as always, formulas: Q equals mc delta T, knowns and unknowns. Mass still hasn't changed. The C for steam is now 2,000 joules per kilojoule degrees Celsius. Delta T, TF minus TI. So TF is 120 degrees. It started at 100 degrees. So our change in temperature ends up being 20 degrees Celsius. Sub in our numbers here. So we get 2 kilograms times 2,000 joules per kilogram degrees Celsius times 20 degrees Celsius. Degrees Celsius cancels out, kilojoules cancel out. We end up with 80,000 joules. All the rest of our energies are in kilojoules, so we're going to divide by 1,000, moving our decimal place over 3. So we end up with 80 kilojoules. Okay, that's our last calculation like that. The last thing we need to do is add all 5 of those numbers together so we know how much energy was needed. So our total, we had 83.6 plus 668 plus 836 plus 4,520 plus 80 altogether gives us a grand total of 6,187.6 kilojoules. And that makes sense. You're going to need to add a lot of energy to turn a block of ice, a 2 kilogram block of ice, into steam. All right, that is the end of this lesson. We will see you tomorrow in class.